For the Oprim, like if it's not just Oprim, it's all of us. The window that, or like you click on Oprim as a person, talk to it, won't just be her, it'll be all of us.
Yeah. Okay. Should we start?
We should turn off the light.
Sure.
Should I share my screen?
Yeah. Yeah. I think I did. Yeah, you can do that.
Okay. All right, is everyone able to see that? Okay, beautiful.
So, are you ready? Good. So it's my great pleasure to introduce Yvon Verberne. I'm not sure if I'm pronouncing your name correctly.
You are.
Great. From Georgia Tech, and also she does ICM this semester. She's going to tell us about automorphisms of the fine curve graph. Thank you.
All right, thank you so much for the introduction, and thank you to the organizers for giving me the opportunity to speak today. Today, I want to discuss work which is joint with Adele Long, Farb-Margalit, Anna Pham, and Claudia Yao. And this work was done in conjunction with the Georgia Tech REU, which took place this summer at the Georgia Institute of Technology. So an overview of the project that we looked at today was we were looking at the fine curve graph, and we were specifically looking at what the group of automorphisms of the fine curve graph would be. So what we were able to find is that the group of automorphisms of the fine curve graph or surface is isomorphic to the group of homeomorphisms of the surface. So in order to get started, we're going to start by discussing the curve graph and some of the various results that we know for curve graphs. So the object that we studied is called the fine curve graph, and it was introduced by Bowden-Hensel-Webb. And the reason why they ended up defining the fine curve graph was because they were studying the group of diffeomorphisms of the surface. And what they wanted to do was see if you can find unbounded quasimorphisms in the identity component of the group of diffeomorphisms of a surface. So the way that they ended up defining the fine curve graph was by allowing the vertices to correspond to essential simple closed curves on the surface. So by simple closed curves, we mean curves that do not self-intersect. And the word essential means that the curve is not going to be isotopic to a point, a puncture, or a boundary component. So if we look at the curves on the surface of genus 2, we can notice that this orange curve here that I'm outlining, you're able to isotope it down to a point. So this is an inessential curve, and so it will not correspond to a vertex of the graph. On the other hand, if we look around this genus, we see that there's two different curves. And while they're isotopic, they're going to each have their own vertex in the fine curve graph. And then we're going to place an edge between two vertices if they correspond to being disjoint.
So a quick question, this isn't homotopy classes of curves. This is all
Curves.
all these are all images of injective mappings.
Correct. So we're not looking, pardon?
Are different parameterizations of the same image? I guess. It's
Yeah,
just the
so this pink curve here and the red curve, even though they're in the same homotopy class, they each correspond to their own unique vertex in the fine curve graph.
right.
The question is that the different parameterization of the same curve, is it the map or a set? That's a vertex.
Sorry, I can't hear the question.
It's a set. It's for the pink curve that you just traced. It's just the image. It doesn't matter how you parameterize it.
Correct.
Decompose with the diffeomorphism of the circle. That doesn't change the point.
Correct. That is the correct interpretation. Okay, so in contrast, the curve graph was defined by Harvey. And for Harvey's curve graph, we were looking at isotopy classes of essential simple closed curves. So in this example, we're once again not going to take any inessential curves, but now the two curves that are surrounding this genus are only going to correspond to one vertex in the curve graph. And once again, we're going to let edges correspond to disjointness. Another object that we're going to need to study this concept is the extended mapping class group. And one way to think about the mapping class group is that it's the group of symmetries of a surface. The more precise definition of the extended mapping class group is that you're looking at the group of homeomorphisms of a surface up to isotopy. And the extended mapping class group, you don't care if the homeomorphism is orientation preserving or not. And we're predominantly going to focus on the extended mapping class group. And every once in a while, we're going to discuss the mapping class group, which is the group of orientation preserving homeomorphisms, but I'll be clear when I'm passing from one to the other. So I want to start off with some of the history that we already know. So one of the celebrated theorems by Ivanov is that the extended mapping class group of a surface is isomorphic to the automorphism group of the mapping class group. So those are the orientation preserving homeomorphisms, which is isomorphic to the automorphism group of the curve complex of a surface. So I want to take a quick minute to see why this theorem could be true. So the first piece of Ivanov's theorem, let's take a look at why the extended mapping class group of a surface could be isomorphic to the automorphism group of the curve graph. So there's a really nice natural map from the extended mapping class group of the surface to the automorphism group of the curve graph. So in particular, if I pick an element of the mapping class group, this is a homeomorphism of the surface. And something we know about homeomorphisms of surfaces is that they're going to map disjoint curves to disjoint curves. So since the edges in the curve graph correspond to disjointness, this means that when we end up applying a homeomorphism to the graph, it's going to induce an automorphism of the curve graph because it corresponds to preserving disjointness. So the work that Ivanov did was to see that this map did in fact have an inverse. So Ivanov was able to show that for surfaces of genus at least 3, this natural map is in fact an isomorphism. Now let's look at the second part of this theorem. So why would the extended mapping class group of a surface be isomorphic to the automorphisms of the mapping class group? So notice that if I take an element of the extended mapping class group of a surface, I can act on the mapping class group via conjugation by the function. So one of the important things that Ivanov was able to show is that automorphisms of the mapping class group have to preserve powers of Dane twists. So notice that a Dane twist, this is a mapping class defined by looking at a curve of the surface, cutting along this curve. Now you're going to break the surface up so it has 2 extra boundary components. I'll twist one of the boundary components and close the surface back together. But the important part about these Dane twists is that you're able to define them just by picking a group of curves on the surface. So since automorphisms of the mapping class group preserve powers of Dane twists, Ivanov was able to prove that this will end up letting us just reduce this question down to a problem utilizing the curve graph. So even though this question about whether the extended mapping class group is isomorphic to the automorphisms of the mapping class group, this really ends up reducing down to a question of the curve corresponding to the curve graph. So a nice takeaway here is that the curve graph ends up being a really nice combinatorial tool that we can use to study the extended mapping class group of the surface and also the mapping class group of the surface. So this theorem by Ivanov really inspired a lot of different theorems. And these theorems came in one of 2 flavors. So the first direction that people studied was they would look at automorphism groups of a simplicial complex which is naturally associated to a surface, and then show that it's isomorphic to the extended mapping class group. So this would correspond to showing that the extended mapping class group of a surface is isomorphic to the automorphisms of some simplicial complex. So you can see why people were inspired by this theorem that the automorphism group of the curve graph is isomorphic to the extended mapping class group. Another direction that people studied is they would take the automorphism group of some normal subgroup of the mapping class group and show that this is isomorphic to the extended mapping class group. Because something to notice is that the mapping class group of a surface is itself a normal subgroup of the mapping class group of the surface. So because of how many theorems were done in these 2 directions, Ivanov ended up creating the following metaconjecture. So Ivanov stated that to every object naturally associated to a surface and having a sufficiently rich structure, that it would have the mapping class group as its group of automorphisms. So there's been a lot of work done to prove that this metaconjecture holds. So I want to give a brief overview of some of the evidence for the Ivanov metaconjecture. So work of Ermac studied the complex of non-separating curves. This is the complex which is defined by taking the isotopy classes of non-separating curves as the vertices. And we say that a curve is non-separating. If I look at the curve on the surface, I cut along it and my surface stays in one piece. And so Ermac was able to prove that the group of automorphisms of the complex of non-separating curves is in fact isomorphic to the extended mapping class group. Brendel and Margalit in turn looked at the complex of separating curves. So the complex of separating curves takes the isotopy classes of the essential simple separating curves of the surface. So a separating curve is a curve on the surface where if I cut along it, my surface now breaks into two separate pieces. And Brendel and Margalit were able to show that the complex of non-separating curves satisfies the Ivanov metaconjecture. McCarthy and Papadopoulos studied the truncated complex of domains. So the truncated complex of domains has the vertices being isotopy classes of domains, where domain is a subsurface of our original surface. And what you want is that there are not that none of the subsurfaces correspond to pairs of pants, where two of the boundary components of the pairs of pants are boundaries of your original surface. So that would be, for instance, taking a surface of a 5 times punctured sphere, where instead of taking the punctures, you take them all as boundary components. And then you just take a curve around through the boundary components. So those aren't the surfaces that you want to look at. And the edges for this complex would be disjoint domains. And this object also satisfies the Ivanov metaconjecture. Work of Ermac, McCarthy, and DeSarlo studied the arc complex, where the arc complex is defined where the vertices are isotopy classes of essential simple proper arcs, where an arc is considered to be proper if the endpoints are either on the boundary or at a marked point. And the arc complex also satisfies the Ivanov metaconjecture. Work by Korkmaz and Papadopoulos studied the arc and curve graph. And this is an object where the vertices are either simple essential proper arcs or essential simple curves. And a final example is by Bowden, who studied the complex of strongly separating curves. So the complex of strongly separating curves considers a subset of the curve graph so that the curves have a specific property. So in particular, the curve is considered to not be strongly, the curve is considered to be strongly separating. And Bowden was able to show that this also satisfied the Ivanov metaconjecture. So here we see some evidence for looking at simplicial complexes and showing that the automorphism group of these simplicial complexes is isomorphic to the extended mapping class group. On the other hand, there's also a lot of evidence for normal subgroups of the mapping class group having their automorphism group be isomorphic to the mapping class group. So one of the first examples was by Farb and Ivanov, who studied the Torelli group. So the Torelli group is a subgroup of the mapping class group where we consider the mapping class elements that fix the first homology. Another way to think about this is that this is a subgroup of the mapping class group that we generate by taking Dane twists about separating curves or Dane twists around bounding pairs. And Farb and Ivanov showed that the automorphism group of the Torelli group is isomorphic to the extended mapping class group. Brendel and Margalit studied the Johnson kernel. So the way that I think of the Johnson kernel is that it is a subgroup of the Torelli group where I'm only taking the Dane twists about the separating curves. And Brendel and Margalit were able to show that the Johnson kernel also satisfies the Ivanov metaconjecture. And Britson, Patet, and Sauto looked at every single term of the Johnson filtration. So the Johnson filtration is an infinite sequence of nested normal subgroups in the mapping class group. And the Torelli group and the Johnson kernel are the first two elements in the sequence. So Britson, Patet, and Sauto were able to find an infinite sequence of normal subgroups, and each of these elements had that their automorphism group was isomorphic to the mapping class group. So from this example, we see that there are so many examples of normal subgroups that satisfy the metaconjecture. So a question that would be natural to ask is whether all non-trivial normal subgroups of the mapping class group would satisfy the metaconjecture. Work by Damani, Giradel, and Osen were able to show that this is not the case. So what they did is they constructed examples of infinitely generated free normal subgroups of the mapping class group whose automorphism group is not isomorphic to the mapping class group. So taking a closer look at the work by Damani, Giradel, and Osen, something to notice is that all of the examples have that their non-trivial elements in the subgroup are pseudo-Anosov mapping classes. Pseudo-Anosov mapping classes are the mapping classes that mix the underlying surface in a very complicated way. Another way of thinking about it is that the support of a pseudo-Anosov mapping class is the entire surface. So what this means for us is that the support of every non-trivial element is the entire surface. So a natural question to ask is whether the Damani, Giradel, Osen subgroups are the only ones which will not satisfy the Ivanov metaconjecture. So in work by Brendel and Margalit, what they did is consider elements with small support. So we say that a subsurface is small if it is contained in a non-peripheral subsurface of genus K with connected boundary, where the number of genus is bounded by the genus of the surface over 3. So we end up saying that a mapping class element has small support if its support is on a subsurface which is considered to be small. So in work by Brendel and Margalit, they were able to show that if N is a normal subgroup of the mapping class group, which contains at least one element of small support, then the automorphism group of this normal subgroup will again be isomorphic to the extended mapping class group of a surface. So now that we've gone through some of the history, I think we're ready to look at the main theorem. So recall that the fine curve graph is the graph where the vertices are the essential simple closed curves and where the edges correspond to disjointness. So if we're looking at the automorphism group of the fine curve graph, notice that it's not natural to think that it's going to be isomorphic to the mapping class group. So for all of the evidence that we saw that a graph is going to be isomorphic to the mapping class group, the word isotopy or homotopy came up. And so it's natural to see why the mapping class group would come up as the isomorphic subgroup, because the mapping class group is the group of homeomorphisms up to isotopy. So if we get rid of the word isotopy for this fine curve graph, it's natural to ask whether the fine curve graph is going to be isomorphic to the group of homeomorphisms of a surface. So one of the ways that we can see why this is a natural question to ask is to just study what does a homeomorphism of a surface do to a collection of curves on the surface. So on the top left, notice that I have a surface of genus 3 and I have a collection of curves on the surface. And when I do a homeomorphism of the surface, something that we discussed before is that every single that homeomorphisms of the surface will preserve disjointness. So if we look below on the bottom left, we see a subgraph of the fine curve graph, which is corresponding to the curves in the surface above. When we do the homeomorphism of the surface, since disjointness is preserved, we see that if there's an edge on the surface, it's going to stay an edge in the fine curve graph. So we end up seeing that the homeomorphisms of the surface induce an automorphism of the fine curve graph. So like we saw with the curve graph and the mapping class group, here we see a natural map from the group of homeomorphisms of a surface to the group of automorphisms of the fine curve graph. So together with Long, Margalit, Pham, and Yao, we were able to show that for closed surfaces of genus at least 2, the natural map from the group of homeomorphisms of a surface to the automorphisms of the fine curve graph is in fact an isomorphism. So what we know is that every homeomorphism of the surface induces an automorphism of the fine curve graph. So what we will need to show is that every automorphism of the fine curve graph induces a homeomorphism of the surface. So because we're working with the fine curve graph, there are going to be some pretty large difficulties that come up, which do not happen in the case of the curve graph. So if we consider two vertices of the fine curve graph, we can see that they can bound uncountably many bigons when we consider them as curves on the surface. And they can also intersect uncountably many times. So what this means for us is that a lot of what was used to study the curve graph of a surface can no longer apply in the case of the fine curve graph, which means that we need to create new tools and ways to study the fine curve graph than we had for studying the curve graph of a surface. So our main goal in studying a question like this is that we want to use collections of vertices to encode points in the subsurface, in the corresponding surface. So the reason why we need to be able to pinpoint points on the surface is because if we have a surface and we have a homeomorphism, this homeomorphism tells us where every point of the surface gets mapped to. And what we would need to be able to do is take an automorphism from the fine curve graph and use that to tell us how we can take any point on the surface and map it to a different point on the surface. So this ended up being a really difficult question to ask in the case of the fine curve graph. However, there's work of Farb-Margalit where they studied a complex called the extended fine curve graph. And in the case of the extended fine curve graph, finding a way to encode points on the surface was considerably easier than finding a way to do this in the fine curve graph. So the extended fine curve graph is defined to be the graph where the vertices correspond to the simple closed curves of a surface. So now we see why this orange curve is drawn on the surface. This is an inessential curve, but in the case of the extended fine curve graph, we do include this as a vertex of the surface. And once again, edges will correspond to whether two curves are disjoint in the surface or not. So in work by Farb-Margalit, they were able to show that for any surface without boundary, the natural map from the group of homeomorphisms of a surface to the automorphisms of the extended fine curve graph is an isomorphism. And the main tool that they use to prove this theorem is the idea of convergent sequences on a surface. So Farb-Margalit defined a convergent sequence to be a sequence of vertices of the extended fine curve graph, which converges to a point on the surface if every neighborhood of that point will contain all but finitely many of the curves in the sequence. So what this means is that you essentially have a collection of curves on the surface which are converging down to a point. And so it's essentially like a target board, which is leading us to a point on the surface. So what Farb-Margalit did was they found a way to encode these convergent sequences on a surface into information about the extended fine curve graph. So what Farb-Margalit were able to show is that automorphisms of the extended fine curve graph preserve convergent sequences. And in particular, they were able to show this by showing a correspondence between the topology of the surface and the graph theoretical information that you can find in the extended fine curve graph. So if we take a convergent sequence on the surface, they were able to show that this is in direct correspondence with the following graph theoretical information. So the first piece of graph theoretical information is that there will always exist a vertex A, which intersects the tail of the sequence. And so when we say that the vertex intersects the tail of the sequence, we mean that this vertex, so this curve in the surface, has to intersect infinitely many of the curves in the convergent sequence. So in particular, this means that it must pass through the point X that the convergent sequence is converging towards. The second piece of information that we see is that if A and B are distinct vertices, both of which intersect the tail, then they too must intersect. So putting 1 and 2 together, notice that we can see the following thing in the fine curve graph. If we have a vertex A that intersects the tail, that means that the vertex A will not have any edges with infinitely many of the curves in the convergent sequence. In addition, if A and B are distinct vertices, both of which intersect the tail, then both of those vertices will not have edges with infinitely many of the curves in the convergent sequence, but will also never have a curve, will never have an edge between A and B. So this graph theoretical information, when you end up doing an automorphism of the extended fine curve graph, all of this graph theoretical information ends up staying preserved. Because when you do an automorphism, if you don't have an edge between two vertices, you will once again not have an edge between two vertices. So this means that when I do an automorphism of the extended fine curve graph, I will be taking a convergent sequence to a second convergent sequence. So what this means is if the first convergent sequence converges down to a point X, and this gets mapped to a convergent sequence, which is converging to a point Y, I can see that this automorphism of the curve graph is sending the point X on the surface to the point Y on the surface, which is going to allow me to build a homeomorphism of the surface, since I can do this for every point. Since for every point, I can define a convergent sequence using vertices in the extended fine curve graph. So using this lemma by Farb-Margalit is how they ended up building the inverse map from the group of homeomorphisms of a surface to the automorphisms of the fine curve graph. So in particular, they found a map going from the automorphisms of the extended fine curve graph to the group of homeomorphisms of a surface. So now what we want to do is we want to take the work by Farb-Margalit and we want to extend this to the fine curve graph. So in particular, our goal is going to be to find the homomorphisms from the automorphism group of the fine curve graph and to find a map to the automorphism group of the extended fine curve graph, because we already know that that object is isomorphic to the group of homeomorphisms of a surface. And so the main tool that we're going to use is something which we call a Bigon pair. So if we take two vertices of the fine curve graph, we say that they form a Bigon pair if the intersection between the two curves of the surface is a non-trivial closed interval and the curve C and D are homotropic. So if we look at this surface here, notice that we have a curve which travels along the outside of the genus and then goes slightly below. We have a second curve which intersects the first curve with an interval and then travels above. So this is what we mean when we say a Bigon pair. If both of the curves in the Bigon pair are non-separating, we will call the pair a non-separating Bigon pair. So in this example, if you take one of the curves and you cut along it, our surface will stay in one piece. But something to note is that every non-separating Bigon pair ends up being separating. And by this we mean, if we cut the surface along both of the curves in the Bigon pair, notice that this middle circle ends up being cut out. So what we end up seeing is that we have these discs that are removed when we cut along the Bigon pair. And these discs exactly correspond to a boundary component, which in turn corresponds to an inessential curve on the surface. So what we're able to do is use Bigon pairs to encode the inessential curves on a surface, which will help us to encode a map from the automorphisms of the fine curve graph to the automorphisms of the extended fine curve graph. So a lemma that we had to show along the way is that automorphisms of the fine curve graph preserves the set of non-separating Bigon pairs. So the reason why we wanted this lemma to hold is the same reason that Farb-Margalit wanted to show that convergent sequences are preserved by automorphisms of the extended fine curve graph. Because notice, if I have a Bigon pair is able to determine an inessential curve on the surface. What you would ideally want is that an automorphism of the fine curve graph would send an inessential curve to an inessential curve. And since non-separating Bigon pairs are preserved, this means that if I have a non-separating Bigon pair in the fine curve graph, and I do an automorphism, it'll be sent to a separate non-separating Bigon pair, which means I can have a corresponding inessential curve sent to a different inessential curve on the surface. And what we do is we end up using this lemma to define a homomorphism from the automorphisms of the fine curve graph of a surface to the automorphisms of the extended fine curve graph of a surface. However, showing that this homomorphism is well-defined is very difficult. And the way that we overcome this difficulty is by using something that we call a sharing pair. So if I have a pair of Bigon pairs, AB and A prime B prime, we say that they are a sharing pair if the corresponding arcs in SG1 have disjoint interiors. So the way that I like to think about this is when you look at the two Bigon pairs, so here we have one Bigon pair that goes around one part of the genus and one that wraps around the second part. Notice that if I take a small neighborhood around this inessential curve that's defined, it breaks it up into two different arcs. And this holds true for for each of these examples, even the ones that go tangentially towards the same point on the inessential curve, because by taking this small neighborhood, it breaks it up into two different arcs. We say that a sharing pair is linked if every boundary parallel curve in SG1 sufficiently close to the boundary intersects the two arcs alternately. So another way to think about this is that if I'm traveling along this inessential curve, I'm going to see an arc corresponding to the first Bigon pair, an arc corresponding to the second Bigon pair, then back to the first and back to the second. So it's just that they alternate so that they're linked. And with Long, Margalit, Pham, and Yao, we were able to show that automorphisms of the fine curve graph ends up preserving the set of linked sharing pairs. So if we have one linked sharing pair and we look at an automorphism of the fine curve graph, it will send the linked sharing pair to another linked sharing pair. So now what we can do is use this lemma to show that the homomorphism that we're going to define from the automorphisms of the fine curve graph of a surface to the automorphisms of the extended fine curve graph is well defined. Okay, so let's start by defining the homomorphism that we want to show is well defined. So if I take an automorphism of the fine curve graph, I'm going to define an automorphism of the extended fine curve graph as follows. So if I have a curve that's an essential simple closed curve, I'm just going to let the map in the image be the same as the map in the domain, because the curves, the essential simple closed curves show up both in the fine curve graph and in the extended fine curve graph. On the other hand, let's consider an edge, a curve on the surface that's inessential. What I'm going to do is I'm going to take a Bigon pair, which determines this inessential curve, and I'm going to let the automorphism in the image correspond to the inessential curve, which is defined by taking the automorphism applied to the Bigon pair. So the curve is going to be defined by our automorphism applied to C and our automorphism applied to D, which will once again give us a Bigon pair. So to show that this is well defined, all of the difficult work lies in showing that the piece where we're mapping the inessential curves is well defined. So let us suppose that C prime and D prime is a different Bigon pair determining the same inessential curve. What we're able to do is find a sequence of linked sharing pairs. So in particular, I'm going to take a sequence C0D1, C0D0, and C1D1, which will form a linked sharing pair. And then I'll find a different linked sharing pair where I take C1D1 with C2D2 and form another linked sharing pair. So to prove that this path exists takes a little bit of extra work because we'll have to pass into the extended we'll have to pass to the fine arc graph, which is similar to the arc graph of the surface, because these linked sharing pairs are able to be defined based on the arcs corresponding to the linked sharing pair. But because we're able to create this path, and for each of the two elements in the path that are right next to each other, forming the linked sharing pair, and automorphisms of linked sharing pairs sends you back to linked sharing pairs, we know that we're going to end up being well-defined. So automorphisms preserve the set of linked sharing pairs, and this is what tells us that this map has to be well-defined. So our final step has us compose our natural map, which was the map from the group of homeomorphisms of a surface to the automorphisms of the fine curve graph, with our well-defined homomorphism from the automorphisms of the fine curve graph to the automorphisms of the extended fine curve graph. And lastly, we'll compose this with the map by Farb-Margalit, which tells us that there's a map from the automorphisms of the extended fine curve graph to the group of homeomorphisms of a surface. So what we were able to show is that for closed surfaces of genus at least 2, the natural map from the group of homeomorphisms of a surface to the automorphisms of the fine curve graph is an isomorphism. Another object we studied, which I alluded to before, is an object called the fine arc graph. So the fine arc graph is defined to have vertices, be the essential simple proper arcs, where proper means the endpoints are either on the boundary or at a marked point. And the word simple, again, means that it doesn't self-intersect. We're going to place an edge between two vertices if the two arcs are disjoint. Together with Long, Margalit, Pham, and Yao, we were able to show that for any surface of genus G with at least one boundary component, the fine arc graph is connected. So the way that we were able to prove this is by utilizing the fact that the arc graph is connected. So the arc graph of a surface is defined to be the isotopy classes of essential simple proper arcs. And it was proven that the arc graph is connected. So since the arc graph is connected, we know that for any two curves, which are not isotopic, that there's going to be a path between them. So something to notice is that there is a simplicial map from the fine arc graph of a surface to the arc graph of the surface, which is given by taking isotopy classes. So the work that is left for us is that we need to be able to show that if we have two isotopic essential simple proper arcs in the surface, that we're going to be able to find a path in the fine arc graph connecting the two. Because again, since we know that the arc graph is connected, we're able to use that to bring any other path together once we know the two isotopic essential simple proper arcs also have a path connecting them. So the proof is as follows. We have two arcs in the fine arc graph and they're going to be isotopic. So let H be the isotopy from A to B. So for any time t, we're going to let A sub t be the image of this interval cross t. Sorry, there's a small mistake here. This should be an interval, not a closed loop. So if I pick a curve in the fine arc graph, I'm going to define I sub c to be the times where A sub t is disjoint from C. Each of these I sub c's are open. So what I'm able to do is find a sequence of open intervals which end up covering 0, 1. So there is a way to choose each of these arcs so that I'm able to find finitely many, which end up covering the time interval 0, 1. So we'll let T naught be 0 and we'll let Tk plus 1 be equal to 1. And for any other I, we're going to let T sub I be an element in the intersection between I and I plus 1. So what we did is we purposely chose the arcs C naught to Ck to be so that we only need finitely many, and that between any of these two intervals, there's some amount of overlap. So for any of these i's between 0 and k plus 1, I'm going to let a sub I denote a sub t sub I. So something to notice is that for each pair, ai and ai plus 1, you're going to be disjoint from ci purely because of this intersection here. And from the definition, AT is going to be disjoint from CI. So this means we're going to create a path that starts at A naught, goes to C naught, goes to A1, goes to C1, and so on and so forth until I get to CK, which gives me my desired path. So by building these sets, we're able to find a nice way to end up going between two things, which are going to end up being disjoint. So we can build a nice path from from an arc A, which is isotopic, to an arc B. So with Long, Margalit, Pham, and Yao, we were able to show that for any surface of genus G with at least one boundary component, the fine arc graph is connected. So there are still a lot of open problems in this direction that one could ask. For instance, is the automorphism group of the fine curve graph of a surface isomorphic to the group of homeomorphisms of a surface when our surface is the torus? So when our surface is the torus, the edges will no longer correspond to disjointness. They're going to correspond to intersection number 1. So you're going to put an edge between two curves in the fine curve graph if they intersect precisely once. So the reason why we end up having to take this definition over letting edges correspond to disjointness is because for the torus, if the edges correspond to disjointness, your graph isn't going to be connected. Since all of our tools end up using the fact that our edges correspond to disjointness, is there some way to take our work and to have it actually work for the torus? Or do you need entirely new tools in order to prove that the automorphism group of the fine curve graph of a torus is isomorphic to the group of homeomorphisms of a torus? Another question you can ask is, we only looked at closed surfaces of genus at least 2. What happens if we start to puncture the surfaces? Does the result still hold? What if we look at non-orientable surfaces? So all of our surfaces of genus G that we studied are surfaces that we know to be orientable. What if I add a crosscap to the surface? Am I still going to get that the automorphisms of the fine curve graph of this non-orientable surface is isomorphic to the group of homeomorphisms of a surface? And if so, I would be really interested to see what types of tools you have to use to get this to work in the non-orientable case. And what if our surface is of infinite type? So all of the surfaces that we looked at have finitely generated fundamental group, but there are classes of surfaces that have an infinitely generated fundamental group, and these are called surfaces of infinite type. Are we able to say something similar for these surfaces of infinite type? And a final question that I want to close on is, for which simplicial complexes, which I'll denote SCS, associated to a surface S, have that its automorphism group is isomorphic to the group of homeomorphisms of a surface? So we noticed that when they were studying the curve graph of a surface and different simplicial complexes that are affiliated with this curve graph, that you always get that the extended mapping class group is isomorphic to the automorphism group of that curve complex. So what happens if I take all of the simplicial complexes that we know to be isomorphic to the extended mapping class group, and I remove the word isotopy from each of the definitions? So for instance, what if I have an extended separating curve graph? instead of taking the isotopy classes of essential simple separating curves, I just let the vertices correspond to the essential simple separating curves. Am I going to get that the automorphism group of that graph is isomorphic to the group of homeomorphisms of a surface? Or what does happen there? So I'm going to end the talk here. Thank you so much for your time.
Any questions from the If there are no questions? Thanks, Yvon. Oh, okay. Hey,
Thank you.
Thank you for having me.
thanks. Hey, sorry, I was getting over there and I didn't see you, and now I'm not looking at the camera. How are you?
I'm good. How are you?
Let me stop recording first. Now I just remember.
Okay.